Okay, let's get going and start on our first equivalent resistance problem. Starting out with something kind of simple, I want to remind us of our equations. We have two equations for equivalent resistance for series and parallel, and then V equals IR is another relationship that we have that's known as Ohm's law. Even though that's called a law, it is not. It only applies to certain materials. Hopefully, I think your book did a pretty good job of talking about that. That there are a select set of materials that are known as ohmic materials that have this behavior. There are a lot of materials that don't have this behavior. Because of our math limitations in this class, we only look at really well-behaved systems. So we're just going to look at ohmic conductors. Okay. Let's get started with this problem. So what we want to look for when it comes time to simplify a circuit like this is we want to look for either series or parallel connections. And if we look at this circuit that we have right now, I don't have a whole lot of choices as far as series or parallel. It you can There are many, many ways of having components wired that are neither series nor parallel. So right away, what I'll see though is I will see these two resistors here and that those are wired in series. So series means same current, right? So those two resistors would definitely have the same current. They're connected by just that one wire there. So they must have the same current. Okay, so what I can do is I can replace those with an equivalent resistor. These are in series, so I can replace them with a resistor that's equivalent, which is just simply their sum. So these guys here would be replaced. I'm going to do this in the video just since I have the ability to do this by erasing and then replacing. So these two, the 3R and the 2R, I can get rid of those and I can replace them with just one 5R resistor. So first I'm going to put this wire back here, and then I'm going to change this to 5R. Okay, so I've done my first simplification. Now I need to look and see, well, what's next? What could I do next? And I see that I don't have any series here, but I do have a parallel relationship, and that parallel is going to be, so I'll take a moment and look for that. These two here are in parallel. So parallel means same potential difference, right? So I'm looking for that. A way that I can know that these are same potential difference is I can see that on the top side here, they're connected to the same wire here. And actually this wire goes all the way over there. And everywhere that I've highlighted that wire in yellow, it's at one potential value, at one elevation. So elevations in our circuits only change when we cross through some component that is either dissipating or being a source of energy. Resistors, when they have current moving through them, they dissipate energy. So they're an energy drop, therefore a potential drop. Okay, more on that to come. What I want to draw in here is I'm going to change up the color here and show us that these two resistors, the R and 5R resistors, they both go from here. I would have yellow to green. So yellow is some elevation, green is some different elevation. And both of these resistors, therefore, undergo the same potential difference. Okay, so since that's true, that must mean that they're wired in parallel. I want you to be able to identify parallel not just by like the shape of lines, but conceptually by what's going on. So these two are wired in parallel. Um, I'm going to take away some of my highlighting here, and I can replace those two then with their parallel equivalent. So remember, let me put this back. Whoops. Um, this, I'm talking about these two resistors, the R and 5R resistors right now. I'm talking about these two right here. So if I simplify those there, what that will look like is 1 over R plus 1 over 5R, right? That is going to be equal to, I'm going to let you do common denominators and all that business, 6 over 5R. So that means the equivalent resistor here, this is what I'll say, my equivalent resistance is equal to 5R over 6. All right, you want to get really handy with these types of calculations. So I'll probably say that again, but I mean it. Get really handy with these types of calculations. And we're not doing decimal equivalents or decimal approximations. You should be able to find a common denominator. If that's a skill you don't have, then I want you to get it now. Cool. All right, so we're going to then replace these two resistors, and I'm going to go ahead and replace this whole wire here. We can just take this whole thing out, and replace it with this 5R over 6. So I'll put that in there. Okay. Now I look at my circuit again and I ask myself, okay, what can I simplify here? And you might see, maybe it's a little bit obvious that these two are wired in series, right? They would have the same amount of current going through them. Doesn't matter what the wire is shaped like. They're connected by one wire. So those are in series. So for that series, that's just the sum. So that's going to be 5R over 6 plus 2R. So that gives me 17R over 6. I can replace those with a single resistor. That's just 17R over 6. So I'm going to go ahead and I'll take this out and that out there. And then we'll fill this back in with a wire. And this is 17R over 6. Okay, cool. Now we're getting somewhere. We can see that if I continue to look at this, now I have the 4R and 17R over 6 wired in parallel. Same potential difference. I could do the highlighting that I did previously, and I would find they both go from some color to some other color, right? So that those two are in parallel. And if they're in parallel, then I can make that calculation there. So 1 over 4R plus 6 over 17R. That's going to be equal to 41 over 68R, but I'm not done then because I have to invert that, right? So my R equivalent there is going to be equal to 68R over 41. Have some workflow there that works for you. Notice that I use arrows. Be careful not to just connect everything with equal signs when they're not equal. Okay, I'll usually see that in your work, and it's just not good form. It's incorrect, right? This isn't equal to R equivalent. It's equal to 1 over. So I have my R equivalent for this pair, this parallel pair here. So I can go back and start taking care of that. I can get rid of this, this, this. And now I'm left, oh, no, I need to change the value here. So this guy is 68R over 41. All right. And now I have a pretty simple situation here where I have 68R over 41R and then my battery. So I can go ahead and find the final equivalent resistance here. These are in series, so they'll just sum. So my final one is just going to be that R plus 68 over 41R, which gives me 109R over 41. So I'm going to finish this with a drawing so you can see here. So what this does is it gets rid of this, and I didn't mean to do that. And let's see, 109R is what I want to change that to there. So this is only now one equivalent resistor, so we can just model it that way. That equivalent resistor is equal to 109R over 41. This question, notice, is asking me to determine the current through the battery. So that's what I want to find here. In order to find the current through the battery, my notation for battery current tends to be I naught, so I'm going to start using that now. You'll see me use that. Is equal to the potential divided by the equivalent resistance. In this case, this battery potential is given as E. That's notation we use when we're talking about the potential value of an EMF. And I'm dividing this by the equivalent resistance for the entire circuit, right? So that's going to be E times 41 over 109R. So my current is going to be, I'll do this down here. My current is equal to 41E over 109R. That's my final answer there for battery current. Okay, so that was hopefully just a little introduction to this first one. Let's move on now and do the second one. And if this, actually what's best for you to do is we'll move to the second picture and you pause the video, work through it completely on your own, of course, and then turn the video back on and walk through it if you had questions about it. Usually this isn't super conceptual for the most part. Recognizing series and parallel is a concept piece. And then students sometimes have to clean up their habits when it comes to dealing with fractions, but that's probably a good thing to do if you need to. So let's look at the second scenario here, and we're just going to run through the same steps with just a few more resistors here. And I have more choices starting out as far as what I would want to take care of, what I would want to simplify. So let's look at those real quick. Right off the bat, so you're just looking to at first identify series or parallel. And so right at first, I can see that I have these three there, right? Those are in series. Series means same current. Those three would all have to have the same current through them. There are no junctions between them. These two would also have to be in series. No junctions there. This 2R on the bottom wouldn't be included in that because notice that there's a junction right there. So we wouldn't include that 2R. But we have these series cases that are good places for us to start. So that's probably where I would begin. This series one right here, those are, we just simply have to sum those guys. So we'll have R plus 2R plus 2R. So that just gives me 5R. That one's nice and simple. And then this one here, R and 3R, right? That one's going to be pretty simply 4R. So I just summed those there. So I'm going to go back here now, and I'm going to replace. I'll get my eraser, and I'm going to replace these guys. I'll take this one out, and replace with 5R up there. And I'll replace with 4R. So you don't have the nice eraser. You'll just draw several different versions of drawings. That's what I do in the written solutions. So I would say if you're working on paper, you want to do something like that. So this here is 5R. This one's 4R. So you just put in the equivalent resistor basically where the other resistors were. You replace the network of resistors with the equivalent resistor. So we can call this R equivalent 1 or something, right, to be good about our notation. So now I do that, and then I look at my situation again, and I see what I can recognize here. So let's look at that. And I see that these two are in parallel, right? Same potential difference, either side of those. If I were to highlight my different values of potential, I would see that, let's just do that super quick. I would go from, say I colored this side here green. I can choose whatever color I want, and say I use this side here yellow, and yellow means some particular elevation value, right? That's a potential value, but we're thinking about it as elevation. And if we're thinking about potential as elevation, then the way to consider these components, be they resistors or batteries, is we're considering them to be stairs because they connect sections of different elevation. Regardless, this 5R and R resistor that we're talking about both go from green to yellow, so they are in parallel. Let me grab just another color here, and I'll shade this right here in. And that shows that the 4R and R resistor are in parallel. They both go from yellow to pink. And if you're wondering why this 2R isn't also, that's because I would need to find another color here for this section of wire, and yet another color for this section of wire. And actually we have one more level in this problem. So this is a slightly different color, I guess. This dark orange would be right there. So all of those colors would represent an elevation, different elevations in my circuit. As I said, we'll do more of this as time goes on, but even right now, you can be thinking about this. This allows us to see different wirings as well. So the 4R and R that I had identified earlier, these two are in parallel. They both go from yellow to pink. And I don't see there's no other yellow pink there, just those pair. So I can replace those as well. So 1 over, I can call this R equivalent 2 here, would be 1 over R plus 1 over 4R. So that gives me 5 over 4R, and therefore equivalent 2 would be equal to 4R over 5. And I'll go ahead and replace those. I think I will take this one out. And that means that we can just get rid of this wire that it was on and just represent it over there where it was with 4R over 5. Okay. So now if I keep looking, I see, oh, I didn't replace this other parallel pair up here, and I want to do that. So I'm going to do that real quick. We found it, but I didn't replace it. So that means that I can take this out. I can take that whole thing out, actually. And then replace that with 5R. 5R over 6, I'm sorry. So that was 5R and R. I didn't do that math yet. So if I were to do that, that would be my R equivalent 3, 1 over R plus 1 over 5R would be equal to 6 over 5R. So, whoops, this is 1 over. R equivalent 3 is equal to 5R over 6. All right. So this would be 5R over 6. Okay. So it takes a little bit of time, but you do the same thing over and over again. So I see two different important possibilities here. One is that these two here are in series. These are in series. And the other is that these three may or may not be a surprise to you. These three are in series. So you might be wondering, what doesn't the battery mess that up? But remember what series means. Series means same current. So the battery is another component there, sure, but the battery doesn't do anything to the current. I mean, the current doesn't increase or decrease. The battery doesn't leak out or anything like that at the battery. So whatever current is going through this wire, that's the current that's going to be going through the wire at a different point. Excuse me. The only thing that changes current is at junctions. So current changes when you pass through a junction. That's where you can have current flow in or out of your wire. Okay, but as long as you're not going through a junction, you know that you have the same amount of current. Okay, so let's solve for these two series sets here. I'll call this one, I don't know, R equivalent 4, and that would be equal to 4R over 5 plus 2R. So take a moment. (14R over 5). So that's going to be those two guys. And then the other series, we're just summing those there. So this is R equivalent 4. That's this one. R equivalent 5. Let's say this one right here. That's going to be 4R plus R plus 5R over 6. Plus R plus 5R over 6. Sure. So that'll be 24. This is different from what I did in my written solution, so I'm just going to do this on the fly. 24R over 6 plus 6R over 6 plus 5R over 6. 35R over 6. Okay, that's going to replace the 3 in series that are on the right. Okay, so I'm going to take a moment. Hopefully, as I'm doing these replacements, you're looking at your own work there and figuring stuff out. Take those out first. So 35R over 6 is what we're replacing with there. And then in this other situation over here, well, I'll get rid of this one here and I'll replace this one 14R over 5. Well, that's easy. Okay. So 14, so there's a 1. It's right at the edge of what I can draw there. So I'll do this up here, 14R over 5. I'll get rid of this. Okay, so now I have my 14R over 5 and my R. These two here are in parallel. I can see my colors have now, my highlighting colors have now changed. I don't have these anymore. So I'll get rid of the different colors down here. And that's what happens as you simplify, is some of your highlighting colors can change a little bit. So I can go back with my highlighter and grab the blue and highlight all of this down here would now be blue, right? That would all be blue. And this up here, we could do all of this as yellow. And this, we could do this whole part there as green. Okay, but what I really was going to get to next was the next simplification, which is these two resistors here would need to be simplified. Those are in parallel, so I'll call that R equivalent 6. So 1 over R equivalent 6 is 1 over R plus 5 over 14R. So that'll be 14 over 14R plus 5 over 14R. So that gives me 19 over 14R. I need to flip that around, right? So that goes to 14R over 19. And that becomes my equivalent resistor for that pair in parallel. Let's go ahead and do that. Okay. Now my circuit's getting nice and simple. Look at that. Kind of cool. So this guy is 14R over 19. And now I just have these two in series. So even though I kind of have left these little pieces of wire, they don't do anything, right? So you can, if it bugs you, you can knock those totally out there. And we really just have like this one loop of current with these two. And now those two are in series. So my final R equivalent here, I'll just call that R equivalent with no subscript. That's going to be 35R over 6 plus 14R over 19. And you got to do some common denominator work in there, but you'll get 749R over 114 here. And that is the equivalent that we get down to with only one resistor. So this is our final equivalent value. And now I can find the current through the battery. So battery current is again going to be my EMF divided by my equivalent resistance for this case. So that's going to be 114E over 749R. That's my battery current.